We're going to start a new section of chapters with chapter 16. So this next set and all the chapters that are on the third test are all very related. Um, and so that can make things easier because it's kind of one continuous developing idea over several chapters, whereas the first two tests kind of uh, chapters will be related, other chapters are not so related to the other ones. So either that's a good thing if you can kind of follow the progression of thought here, or if you get behind, then it definitely can be the hardest test. So I would suggest make sure that you get a good foundation in this chapter, and as we progress, I think things will get easier, as long as you kind of follow what we're going to do here, because it's definitely, these chapters definitely need a certain level of understanding. It's not so much you can just kind of uh, memorize some things. I mean, maybe you can, but I think it's a lot better if you can understand the underlying idea, and then the problems, they make a lot of sense once you kind of understand what's being gotten at here. So so this is a fairly lengthy chapter. We're covering sampling distribution models and confidence intervals. One thing that you need to make sure that you're competent at these next chapters is when you see a problem, you need to be able to decipher if it is a categorical variable or a quantitative variable. Um, and it's not so much that you will approach these slightly different depending on which type of variable it is. That the basic idea is the same, but figuring out the answer and doing the calculations will be different. And especially going to the calculator, we're going to learn a couple of different things on the calculator through these next few chapters. And knowing if problems are categorical or quantitative will make things very easy. So the first thing to point out is whenever you see the word proportion, that means we are talking about a categorical variable. So proportions, meaning percents, these are categorical variables. And in particular, these are actually all binomial variables, or binomial distributions in some sense. Although we're not going to do the binomial PDF like we did in the last chapter, we're gonna do more of an approximation. But proportion means categorical variables. So if we look at this first example, according to the National Center for Health Statistics, 11.6% of all babies born in 1998 were premature. So this is a categorical variable because every baby is either born premature or not. So we have an either or, and that's the way these categorical variables are going to go here. We're not looking at multiple categories. We're just, it's a binomial distribution. So we have two different options. And so in this case, we're going to call this 11.6% is called P, and this is going to stand for the population proportion. And the population proportion is just the percent of the population that is doing whatever it is that we want to do, that we're looking at. Or to put it in terms of what we talked about in the last chapter, P is the probability of success, or the proportion of whatever it is that you're looking for. All right, so to simulate the sampling distribution of a proportion, we draw independent random samples from the population and calculate the proportion for each sample. So whenever I'm in a class and we're talking about this kind of thing, I say that, let's just say that each of us in this class, 30 of us or however many there are, or 100 or 1,000, however many people you get, we each go out and sample 100 people or 1,000 people or whatever, babies in this case, and find out if our sample of 100 or however many it is, what percent of that sample of 100 would be premature or whatever it is that we're looking for. So that's what this means, where we're going to get a sampling distribution. And then, so let's say my sample said 12%, and let's say the first person in the class, their sample said 11.3%, and then someone else said 12.2%. So we're all kind of around that area. We're all kind of around the 11.6%, but we all pretty much get different answers or different proportions. So we're calculating a sample proportion for each sample. The following figure shows the distribution of the proportion of premature babies from a simulation drawing 1,000 random samples of size 100. So we have 1,000 samples. Each sample has a sample size of 100. So we had 1,000 people get a sample of 100 each. From babies born in 1998. And so we see this histogram. We've seen histograms like this before. The main difference here from this histogram or compared to the ones we saw earlier in the course is the ones earlier in the course, the y-axis was measuring individuals. So if you saw this histogram earlier, we'd see 100 here. So that would mean the 100 people or a little bit more than 100 people were in that category. Or in that range of values. But here we see this is looking at number of samples. So it's not 100 people, it is 100 of these samples had a proportion of 11.5 or whatever that is, 12 here. So that's something to keep in mind. We're not looking at individuals, we're looking at samples, and all the samples have the same size. In this case, they're all size 100. So if we look at this histogram, we can still describe it using terminology that we're familiar with. It is symmetric. It is unimodal. It is centered, as you might expect, being centered or symmetric and unimodal. It is centered at the mean, and the mean in this case is P, which is 0.116. And so you might think it's 12. It's a little bit off 12, but it's going to be centered at this population proportion P. Standard deviation, we'll talk about in a minute how to calculate this, but standard deviation is 0.032, and then this follows the normal model. And so we're actually going to be using the normal CDF when we are looking at these probabilities, as opposed to the binomial, because once you get many samples and we get large numbers here, we can approximate it with the normal model instead of using the binomial, which just makes things a little bit easier, or at least it did. I guess maybe not so much now with technology, but that's the way we can approximate these things. So sampling distribution. So like I said, this is centered at the mean. The mean is the population proportion. So the mean of this equals P, and P, like I said, stands for population proportion. And so in this case, P is 0.116. And if you remember from talking about the binomial models, we have Q, and Q is just 1 minus P. So P is the probability of success, or whatever proportion we are looking for. Q is the probability of failure, or it's the proportion that we are not looking for. And so if we do 1 minus P, we get that Q is 0.884. And then N, of course, is our sample size. We're going to use N. And so we can calculate the standard deviation of P hat. And P hat we'll talk about later, but P hat is the sample proportion. And so these are all sample proportions because we drew many samples. And this is talking about, where did my mouse go? This is talking about how many of these sample proportions were in this range, 12 to 12.2 or whatever that is. Actually, that's probably 12.5, but that's okay, whatever it is. And so these sample proportions are going to be denoted by P hat. Another thing to make sure that you're getting comfortable with is these symbols. So we use a lot of different symbols, and the symbols mean very specific things, and they're similar, like you can see P and P hat, but they mean different things. And so it's very important that you keep track of what P means, what P hat means, what N means, what Q means. If we have P hat, obviously we're going to have a Q hat that we can talk about. So that's another thing to make sure that that's going to guide, it's going to aid you as you move through these chapters, knowing what these symbols are talking about. So the formula for standard deviation of p hat, and this is a formula you're going to need to know, but you should use it enough that you're not going to have to work too hard to memorize it, because you're going to use it in many problems. So it's square root of p times q over n. So we're just going to plug those in, and p is 0.116, q is 0.884, and n is 100. And when we plug that in the calculator, we get 0.032, like I said. All right, and so what that 0.032 says is measuring how much are the sample proportions deviating from the mean of 11.6%. And so that's what that means. All right, so next page. Mean and standard deviation. So the sampling distribution for proportions is normal. The variation from sample to sample is called the sampling error, but it may be better to be called sampling variability. So when sampling error is not a mistake, sampling variability. So it's just talking how much are we moving one way or the other from that 11.6. So when does the normal model not work? So most of the time it's going to work, and we're not really going to do problems where it doesn't work. So we just need to check if it does. If it does, then we can do the problem. If it doesn't, then we won't worry about it. So when does it not work? So p being close to 0, close to 1, it doesn't work. And we'll talk about, so when does it work? We'll see kind of the contradiction here of why it doesn't work. For instance, males over 6'8" tall. Sample size of 1,000. If p is 0.001, then only a few in the sample of 1,000 would be successes. And in fact, on average, we'd probably only get 1 out of 1,000. So that's not going to be enough to get a normal model, because you have a whole bunch here at 0, a whole bunch of 1, and then it tapers off pretty quickly. For there's no way for it to be symmetric because you can't have the negatives. So the histogram is going to be skewed right. N is large, but p is too small. And the opposite issue happens if p gets close to 1. Then we'd have all of them over here, and then it'd be skewed left. And so we can't have a symmetric model here if p is close to 0 or 1. So that's something to watch out for. So when does it work? Now, these are the conditions for when we can use the normal model, and you will need to memorize these, but again, you'll probably see these enough to where you won't have to try too hard to memorize them. But first, we have the independence assumption. Check that the data is collected in a way that makes this assumption plausible. And randomization condition. These two are pretty related. If the sample is collected randomly, you can pretty much assume independence. And then we have the 10% condition. Now this one, maybe not quite intuitive. This one may not seem obvious, but the sample size should be less than 10% of the population. Now, why less than 10%? Because if you get more than 10%, if you start sampling 30, 40% of the population and you do that over and over again, then you're basically getting the same people over and over again, and they're not independent at that point. So the 10% condition protects this independence assumption. And then we have the success failure condition. This is really the only one. These three, I mean, randomization, the problems we're going to say is collected randomly, or you can assume that, which indicates it's independent. 10%, we'll talk about how to look at that, but there's no calculating there. It's more of a kind of intuitively going to see this. But the success failure, there should be at least 10 successes and at least 10 failures. So in other words, it's not a negative, that's just a bullet point. So n times p should be greater than 10, greater than or equal to 10. N times q should be greater than or equal to 10. And relating this back up here, if the sample size is 1,000 and p is only 0.001, then your expected number of successes is only going to be 1, and you need it to be more than 10. So that's how that kind of relates back to why this doesn't work. So those are the conditions, and if those are met, then we can do whatever it is that we need to be doing. So we'll pick this up and we'll start on confidence intervals and get into solving some problems on the next video.